Hello, everybody. Happy belated Valentine's Day. Thank you for joining us today. All right, so welcome to AOT. We're happy to have everybody in their hands back there. So if you want to order some food, you can order over there and they will bring it in here. That way you don't have to go out into the restaurant and order and then go back out to the restaurant to go get your food. We have some lovely people to help us out with that. And of course, we have our bar in the back. Definitely get some drinks. And our tip war this month is, what is your favorite space heart? So, of course, we have the lovely heart on Pluto, and then we have the heart nebula. So we have tip jars at our merch table, and we will have some of our volunteers going around getting your votes. So you're welcome to participate in that. In addition, if you guys did not get a raffle ticket before coming in here, make sure you grab a raffle ticket. You basically get a free prize if you win, and we have some really cool merch that you might be able to take home. So if you don't have a raffle ticket, we have our raffle person in the back, Alex, or just go see our merch table and we'll get you a raffle ticket. All right, so our first speaker for the night is a little bit different than our advertisement, but it's different order. So we have Edward Montiel. He earned his BS in astronomy and math from the University of Arizona in 2010. While remaining in Tucson, he spent the next 2 years as a research specialist in Steward Observatory, which is from the Department of Astronomy at the University of Arizona. And he was working primarily on image processing of observations from the Herschel Space Observatory. He is an alumni from LSU. He became a graduate student in 2012 and earned his PhD. His advisor is here in our audience. It's Dr. Jeff Clayton. And he earned it in 2016. And that same year, he moved from Baton Rouge to San Jose, California to start his postdoc at UC Davis with the Echelon Cross Shell Spectrograph instrument team, which flew on the Stratospheric Observatory for Infrared Astronomy, or SOFIA, which he will talk about today. And in 2019, he was hired by the University Space Research Association as an associate scientist with SOFIA, and he earned a promotion to full scientist last year. And he really enjoys doing triathlons and completed a half Ironman. So I give him props for that because I hate running. But please give it up for our speaker. He is on Zoom, so he can't hear you, but we can give a round of applause.
Sure. I'm going to take that as a cue to start talking. I hope my slides are coming through fine. And I'm really happy to be back virtually in Baton Rouge. Go Tigers. On this title slide, it's a cue play, of course, on Dr. Strangelove, since my advisor was Jeff Clayton. Just not plan a movie title. And we'll start at the end. And so I had the honor and privilege of being on the very last SOFIA flight, Science Flight 921, which went over September 28th and 29th of 2022. And pictured there are the people who were on board. There's the two pilots, a flight engineer, a host of other instrument scientists, a safety tech, a telescope operator, and an instrument scientist. And you can also see that there's a gambit of different things. So some people like to do the flight suits. Other people just like to wear regular clothes because sometimes the flight suit's a bit of a hindrance, and it also is hot in Palmdale, California. So this is a astronomy background about light and our atmosphere. I think traditionally everyone, of course, knows that we build telescopes on mountains and put them into space. But there's a whole host of the electromagnetic spectrum, from gamma rays to radio waves, and the wavelengths of light sort of reach different altitudes in our atmosphere. Some make it all the way down to the ground, some get stopped higher up, and others you just have to be in space for. And so as you can see in this image put together space telescope, they put a handy little airplane showing you that at certain altitudes in our atmosphere, certain wavelengths of infrared light come through much easier than they do to the ground. And so an illustration for that in terms of what SOFIA saw compared to, let's say, a telescope on Mauna Kea in Hawaii is you can see for this background galaxy on top there, if you're at 14,000 feet on Mauna Kea, most of that galaxy wouldn't show up as opposed to when we are at SOFIA at our highest flying altitude of 45,000 feet. We sort of are able to thin out our atmosphere by being above 99% of the water vapor, which causes most of that absorption. And you'd be able to sort of start making a more complete image of that galaxy in different wavelengths. The history of airplane astronomy goes back into the late 1960s. They put a 12-inch telescope on a Learjet and flew at least at 50,000 feet and higher, since it was a smaller airplane and designed to fly higher, which then inspired NASA to build the Kuiper Airborne Observatory in the 1970s. It flew for about 20 years and carried a 36-inch telescope, which was mounted towards the front of the fuselage. And then they had this idea of making a bigger plane, which was SOFIA, which is a 747 SP. And we carried a 2.5-meter telescope. So just showing size comparisons. And as the sort of the title talked, the big thing was putting this telescope towards the back of the plane and making a giant 12 by 18-foot hole in the back of an airplane. And so this handy little graphic put together by our outreach team sort of shows how when the doors open, there's a bit of a lift to the front of the fuselage, and air, when the doors open, sort of passes over so that in the air, it's a continuous, even flow across the fuselage of the plane. And also, since this was done 30 years ago, this was sort of the last times when they would actually build scale little models of it and go and put it into a wind tunnel. So these two photos show a model of SOFIA in the 14-foot transonic wind tunnel at Ames. And we've had several visits of SOFIA. So SOFIA nominally lived down in outside of Los Angeles in Palmdale, California, but every so often would visit Ames here in the Bay Area, where the SOFIA Science Center is. And so we were able to get this cool photo in 2008 of the Kuiper Airborne Observatory and SOFIA in their actual, configurations side by side, looking at, and you can appreciate this, how much larger SOFIA is than the KAO. So just some other fast facts about SOFIA. SOFIA is an 80-20 NASA and DLR, which is the German equivalent to NASA project. NASA provided the airplane and a few of the science instruments and staffing, and DLR provided the telescope, some of the other instruments, and some of its staffing for what its needs were. And so there's this cool sort of, I found this old photo, of SOFIA in 1998 with its sort of old United color scheme, and then what they repainted it for when it was actually ready for science flights. SOFIA is a 747 SP, as I mentioned, and we flew between 36 and 45,000 feet. And then I just sort of put on this slide just what the typical crew would be. I believe the smallest crew flight that I was on was about 10 people. The most, if you have like guest observers, we had teachers, which were those airborne astronomy ambassadors, or media or other sort of VIP stuff flew. It could be as much as 30 people on board a flight, which then it starts to get a little crowded, even though we're not your sort of typical plane. It's just there's a lot of extra bodies around. So what kind of science were we doing with SOFIA? What could we do? We had both typical cameras like on your cell phone that saw in the infrared, or we had spectrographs, which are able to divide light up into individual components. I primarily worked with the XES instrument while on board SOFIA. So it's a mid-infrared spectrograph that could separate light up to 1 part in 100,000. But I've also flown with FIFLS, GREAT, Hawk Plus, because I was on those final science flights. A note on the FPI Plus, it was also our guide camera. So it was always mounted on the plane, since that's what the telescope operators would use to sort of capture our science targets and then allow us to track on them. And then we would just rotate out those instruments there. So in the photo at the bottom, I have a photo of XCs on one of the first flights I went on after we had installed it. And basically, after every observing one, we would take off an instrument, put another one on, and get ready for it to fly again. And so that was sort of what was the selling point for why you would want to put a telescope and basically an observatory in an airplane as opposed to a satellite, in that, like JWST, which is out in space at L2, no one, currently is ever going to go out there to fix it if anything terrible were to happen to it. We also, as opposed to sort of like ground-based observatories, we could take our observatory everywhere. There were flights out of Florida, uh, internationally. I guess I have Florida there twice, but we regularly went down to Christchurch, New Zealand. We did one series out of Tahiti, one or two series flying out of Germany, and one series flying out of Chile. And so when you have a telescope that moves through the air, you have to plan and make really detailed of like when you're going to be where in the sky, and of course file flight plans with the FAA. And so on the left there is what our flight planners had to think about, is where any potential restricted airspaces could be during our flight, and our mission planners would check 36 hours, 12 hours, 1 hour before a flight to find out if like, oh, this one patch of air is going to be taken, so don't fly there, we've had to push you a little bit far north than what you planned. And then on the right here, I have sort of highlighted just different sort of flight configurations that we've flown across these. So we can either make these big swooping, rectangular shapes. We can fly north over Canada up to Alaska and the Arctic Circle. Or in the one on the far right, we can just make these sort of really tight spirals over the Southwest. It's just sort of what you need to base off the science observations that are going to happen that night. And the other part is always you need to land back at the airport that we've taken off. So if we actually do, and we're all set and we're aboard a flight, then the main thing after takeoff is door opening. So putting that big hole into the plane that's going to be exposed to the air. And so in this video, this was one of the early door open tests in 2013 when they just opened the door for 2 minutes. It's the main thing that if we aren't able to open the door, then of course we don't get our science. The door is fully automated. Just the pilots push a button upstairs after consulting with the mission directors. I'll talk about what they do more in detail in a few slides. And that door just opens up on its own, and then basically it's flying the plane at that point. A science flight leg anywhere from 30 minutes to 4.5 hours, depending on how long you need to just stay on the source. And everything, in smooth air, everything is great, but we can experience, moderate to severe turbulence can sort of throw the telescope into a safety limit. We have a sort of a hard network on board that could sometimes go down. At least earlier in the mission, it got better over time. Or we have instrument issues. Basically, otherwise, it was just, at that point, we were like any other observatory on the ground, just anywhere from 36 to 45,000 feet high. So in this video simulation of what the inside sort of looks like, this is sort of a modern an early representation of how they thought the inside would look of SOFIA. There's different stations where different people are doing different jobs during the flight. There's sort of 4 principal components that, it's like an orchestra. We're all sort of taking our roles and playing sort of our notes to make a science flight successful. I mostly only flew as either an instrument operator or an instrument scientist, but our telescope, we couldn't be able to do this with our telescope operators or our mission directors or even safety techs sometimes on board for helping us troubleshoot things. And so then the big thing, right, is how do we actually point and keep that telescope stable? And so in this graphic, it shows that we have the telescope isolated from the rest of the plane. Excuse me. It sits on a floating oil bearing. And so what this video on the right is trying to show you is basically when we're in flight, the telescope is stable. If you're not experiencing severe turbulence, basically all those motions and jitters that we're actually seeing is the plane moving the structure around the telescope. It's just perfectly pointed at whatever star or planet or galaxy you'd be looking at. And yeah, it is one of the most was crazy things to think about. It's like whenever we would feel like a bump of, a quick jolt of turbulence, it's like, oh, we moved, but the telescope stayed perfectly still, didn't even notice it, just kept on going and doing its thing. Here's sort of a fisheye look of what the inside of the main floor of SOFIA looks like. So as opposed to like when this was an actual passenger plane, during the remodification, they ripped out everything on the inside and then started retrofitting it to make it, have science stations or where the instrument would go. And so, a lot less people, a lot easier to walk around because you don't have big rows of seats everywhere. So then basically when we're on flight, then if everything's going well, then it's just like your typical night of observing. We would take a break for eating meals, as you can see based on the postdoc there on the left. And on the right is one of my colleagues who found the environment quite cold, so she invested in a giant blanket that she would cocoon herself in, because basically then without all the people and the extra padding that you would normally have on a commercial plane, it gets cold because you're just exposed to the atmosphere nearly at that point, and the plane cools off really fast when you get to altitude. It's about minus 66 degrees Celsius sometimes outside. Not as cold inside, of course, but that outside air does sometimes blast in. Highlighting some of the fun science that came out during the mission. One of these cool sort of images that was put together is what was deemed the Orion Dragon. So in the Orion constellation, there's the Orion star forming region, which is the nearest massive star forming region to Earth. And massive stars play a big role in sort of shaping their natal environment. They make bubbles, veils, other structures sort of as the energy that they're giving off impacts the environment around them. And singly ionized carbon, or C2, is a line of singly ionized carbon is one of the lines that sort of traces the cooling of this material where it's happening. And so with the high spectral resolution from GREAT, we were able to make a map over the full region and also spectra over the full region. So as I pointed out there, more than 2 million measurements of C2 went into this map. And they were able to make this 3D structure from their data to sort of show where the gas was expanding the most, where it's sort of making more filaments. And it's just a really cool thing you can do with some of the instruments on SOFIA. Another one project that I was more personally involved in is this, where we measured mass loss off of a star directly. So this has a double personal connection to me because this is a project I worked on with some collaborators, but also I remember in Rob Hines' Stellar 2 class, I don't know if he's there tonight, but he once talked about how at a conference, people get into a big debate when you talk about mass loss rates, because normally you only can do this through proxy measurements, so like measurements of carbon monoxide. And so people will always point out like, oh, this H2, this mass loss rate you're doing really isn't mass loss because you're not tracing the most abundant gas. So with the XE's instrument, we looked at IRC 10216 or CW Leonis, which is the nearest asymptotic giant branch star. And we're able to actually make a measurement of a line of molecular hydrogen that was predicted to be there 30 years ago, just in about the same shape In that top plot, the velocity axis is flipped from how it's plotted on the bottom, so that's why it'll look backwards. But the signal was there sort of just as predicted at this about the same level. And so we were actually able to make the first measurement for this star or any star in the universe. And this work was awarded Best SOFIA paper of last year, co-awarded. Probably one of the most exciting results that SOFIA had was our detection of water on the sunlit portions of the moon. Casey Hannibal, the scientist who led those efforts, at 3 microns, where there was all this variation seen that could be either from water or what's known as hydroxyl, so just the OH part of H2O. And there's this sort of degeneracy at 3 microns that sometimes OH can mimic what H2O would show you. So she put a proposal in for a forecast where they took spectra and mapping of the moon. And they looked at this Clavius crater in the southern sunlit portion of the moon and were able to detect the signal from water. And when they measured its abundance, it was anywhere from about 100 to 400 parts per million. And that, from their analysis, suggests that this water is sort of trapped in glasses from micrometeorites constantly hitting the moon. And they've turned that into this big survey where they're mapping different regions of the moon in the lead up to the launch of the Viper mission. And they just got more data in May and those maps at the bottom are just the maps that you would get from just like the continuum or the surface of the moon. And they haven't actually started looking for the signal for water yet. And then, of course, the common thing at any astronomy conference is you always get asked, but what about magnetic fields? And so SOFIA could actually help study magnetic fields. So this is where the benefit of being able to upgrade your instruments came into play. So that HAWK used to just be a far infrared camera, but some upgrades by astronomers at JPL turned it into HAWK Plus, creative acronym addition, where now it could also measure the polarization in the far infrared. And so here's just a bunch of cool photos of how we sort of represent the magnetic fields that sort of is likened to Starry Night by Van Gogh. In the top left there is a massive protostar that the magnetic fields are showing how material is being fed down into the star that's forming. And on the right there are some of the 2 highlights of looking at external extragalactic galaxies, Centaurus A in the middle and M82 on the right, just sort of how different the magnetic fields trace sort of what the gas and dust are doing. And another great example of that is looking at the galaxy NGC 1097 in that sort of inner region. There are some HAWK Plus maps, and then when you look and actually plot what the direction the vectors are doing, it shows you that those magnetic field lines are helping transfer gas and dust from outside of the supermassive black hole in the middle down towards the disk in the middle. And so, in summary, I have sort of a poster that we've put it together showing the different cycles and deployments of SOFIA with some science on the bottom there. And on the right there are all 921 science flights that were done from 2013 to 2022. In total, there are about 927 flights that include ferries, ferry flights to different places or check flights, and including the final flight where SOFIA is now living at the Pima Air and Space Museum in Tucson. So if you're out there, visit it. We've made some really cool discoveries on anywhere from our solar system to external galaxies. And currently, we're just in a process of making sure our data is in the best shape it can be and making documentation for other astronomers to use in the future. Thanks. Oh, I am a Magmar guy. I thought the fiery duck was always super cool. That's an excellent question. Pilots that we had were NASA pilots. Some of them flew military, other NASA airplanes, commercial. They were all trained by, there was like a special SOFIA flight school to do it. But I'm assuming if anyone had flown 747s before, then that would have been a leg up for then flying. But yeah, I don't know too much about what ratings the pilots needed. Yeah, so the atmosphere definitely still can play a part. There are still some pretty strong to this plot. So like this line at near 15 microns, that's actually from carbon dioxide in our atmosphere. And no matter how high we would fly, we would never be able to get at. So if you were like looking at 15 microns, it would just look like nothing. But if you sort of look a little bit on either side, so like 13 microns, 16 microns, 17, then maybe you could sort of start to get something and recover it by doing a correction for the atmosphere. In terms of wind, those really don't play because a lot of the wind is just passing over the front of the fuselage, and that's not going to affect the light at all. If it whereas inside and vibrating the telescope, then maybe, but that rarely happened unless there was like a particularly strong turbulence, which at that point the whole telescope is shaking and it probably enters safe mode at that point. There is not. So I think at the end there I had that basically Sophia kind of right now marks the end of airborne astronomy. There is a plan for making sort of bigger infrared telescopes and putting them in space. The decadal survey, which is sort of how astronomy figures out what to do every 10 years, recommended that NASA pursue sort of this new great observatory program over the next 20 to 40 years. So probably not unless for some reason someone really wanted to put something back on an airplane again. Otherwise, yeah, this is probably the last airplane for, I guess I should say, external science. I mean, I'm sure that there must still be planes that like do solar eclipses and fly through totality of that, but nothing for like infrared astronomy. Oh, as in like, why isn't it just looked straight up? Yeah. Right. And so the reason why it's out the side is because a lot of our targets are mostly you need to be able to move the telescope up and down. So if you were just straight up, you would only be able to go right above you. Um, and with this, we were able to, with how they had to configure it, you could go anywhere from about 20 degrees above the horizon to 60 degrees above the horizon. So that gives you more leeway of just looking at different objects wherever they are in the sky. Yeah, so it's the velocity. So light experiences what's called Doppler shift for different reasons. So like it'll either stretch or shorten the wavelength of the light. And so the C2 line emits at 158 microns. And so with great, whenever you detect it at different wavelengths, that tells you about a velocity. So assuming all of this is at one roughly distance, the velocity axis then lets you sort of build this model of the dragon. So training, I guess for me was mainly just sort of what we took what was called egress class, if that's what you mean, unless you mean my background as a scientist. And the favorite part was always just being in the air, and it never got boring. Of like, it never lost its luster. Of I'm on an airplane with a giant 38,000 pound telescope, looking at and taking scientific information. Yeah. So it is a gyroscope and also some oil bearing that sort of sits there. And then there are some other, uh, what they called like the fine body controller. There's some other that our German colleagues put together. There's also something called the active mass dampers, which are like these weights on the back of the primary that try to slide and adjust to make sure that it keeps the mirror shape together. Yeah, thanks. And like I said, it was great to be back in Baton Rouge virtually.
I think it's gonna be a long, long time. And I think it's gonna be a long, long time. And I think it's gonna be a long, long time. And I think it's gonna be a
bear with us. Ready? Testing 1, 2, 3. Did you hear that? Okay. What was that? Testing 1, 2, 3. Test. Okay. He said he can hear you.
Yeah, I can hear you very
Yeah. Okay. Now he can hear me. Now, yeah, he said it came through really well. Okay. So whatever's working, we're good. Yeah. Well, we want to just move forward with the settings right now. All right. We're gonna start. I'm gonna hang up. We're gonna start with the next talk. If you can't hear our next speaker, let me know. Okay.
Yeah, before we
All right.
forward slide, backward slide. You remember, right? Yeah, don't want a lot of buttons. Close the PowerPoint. Can't be pressed if you want. Yeah,
Yep.
top one is the light point. Huh? Yeah. Well, let's see.
All right, everybody. Thank you so much for bearing with us while we work out our tech issues. Hopefully they do not continue. But for you guys, you hear us in person anyway, so we're all good for us. Just a reminder, if you did do trivia, make sure you turn in your cards to the back at the merch table. That way we can go ahead and figure out who our trivia winner is. And don't forget, we have our tip war, food in the back, drinks also in the back. And with that, we'll go ahead and introduce our next speaker. So we have a current LSU student. He is currently a fifth-year student at LSU, and in his free time, he is usually reading science fiction books. So maybe a question about his favorite science fiction book is in the future. So give it up for Kang.
Can everyone hear me well? Perfect. So thank you, Ashley, for the introduction. And hello, everyone. Welcome to my TED Talk on memorization techniques. Just kidding. So before we get started, I would like to clarify on one thing. Though the topic may suggest I am not a neuroscientist, I'm just a dude who had forgotten way too many important things. Most of you will have a better understanding on how to use memorization techniques to remember things more efficiently and retain them for a longer period of time. With that, let's start with a couple of questions. So have you ever had a moment when you needed to remember something important? For example, a mathematical formula or a specific value to a specific constant for a test. And no matter what you do, you just can't seem to get the information to stick. What about someone else's name? Have you ever forgotten someone's name right after meeting them? These are some of the common experiences that I think most of us can relate to. And there's one common thread amongst these information. They are what you would call abstract information. In other words, these are information that cannot be easily visualized, and they are not tangible. As I prepare for this presentation, I try to recall my first ever memory, which bring me back to one fateful, hot day when I was 3 years old. Apparently, as a kid, I loved to be barefooted, which ended up in many a pair of sandals go either missing or misplaced. Knowing this, my parents used to do this thing where they would take off with my sandals right after they dropped me off somewhere. And this brings us to the aforementioned hot day. After some intense napping at my uncle's house, I then had to walk back 2 blocks to home on a very hot day, barefooted on hot concrete and asphalt. So why do I bring this up? So the interesting thing is, so how is it that I can remember this specific day so vividly and yet every now and then have difficult remember my own age? And the reason to that question is the same reason why these memorization techniques work. Most often, information that can be easily stored in long-term memory are attached to an image or an intense emotion. So let's see. It's ironic, right? Talking about memory. Right. So when you see information as combining long-term memories, so these are things that you already have available, stuff like your car, your route to work that you take every day, the numbers 1 to 10, or even the alphabet letters. The trick is you use those long-term memories with these new short-term memories to combine and give what we would call medium-term memory. So all that sounds good and dandy, but how do they work exactly? For this next part, I will need you guys to participate with me somewhat wholeheartedly. The rest of the talk may fall apart if you don't, so please just humor me this one time. So, with that out of the way, in this first exercise, we will try to memorize a list of nouns, and nouns tend to be easier to imagine and store, so let's start there. First, there we go. So in this case, the list of nouns will be your short-term memories, and the object that we will choose from our long-term memory will be your car. So first, let's try to see the car in our mind. And then now imagine squeezing an apple into the front grille of your car. Try to feel the apple crack and open up and its juices pour into your hand. Next, imagine stabbing the carrot on top of the hood of the car. And, try to smell the carrot as it breaks open and feel the carrot go into the hood. And as you look up, you see grain bread in the windshield, and you think to yourself, ooh, the grain bread is gonna ruin my wipers. Next, as you get into your car, you all of a sudden smash a bunch of dry fruits on the dashboard. There's so much dry fruit that you smashed, so much of it that you cannot even see the speedometer anymore. And as you sit down onto the driver's seat, imagine that there are blueberries and strawberries there. Feel the juices seep into your pants. Not comfortable, right? So then, all of a sudden, for no reason at all, you decide to throw some eggs in the passenger's face. And imagine seeing, eggs raining down someone's face. Easy things to imagine. Next, as you do that, you hear someone pour thousands of seeds and nuts into the back seat. Hear the noise that those seeds and nuts make as they're being poured. And when you walk outside your car, you look up and all of a sudden you see that there's a giant orange right on top of the car. I don't know who put it there, but let's just see that it's there. Then, when you open the trunk, you can smell the putrid smell of rotten fish. Imagine opening up your fridge right after Katrina. That kind of smell. And as you look down, you see the image doesn't match here. I couldn't get the dolly to generate a good enough image. But as you look down, you see that your exhaust pipe is filled with broccoli. And on the tip of broccoli, there are smoke in the form of broccoli sprout exuding from the broccoli. And as you look around, you see that the wheels of your car are now made up of bumpy, dirt-colored sweet potatoes. So what have we done so far? We walk out for no reason at all. We shove an apple into the front grill. We stab a carrot peel, wet, right? From strawberry and blueberries. And when you look to the right, you see your passenger face get full of eggs. And as you look to the back, there are still thousands of seeds and nuts there. You can still smell the fish in the trunk, and you can still see the broccoli exuding broccoli sprout smoke from the exhaust pipe. And your wheels, of course, made up of sweet potatoes. Sounds good? So, just yell out, what is on the passenger's side? What is in the passenger's face? Egg, good. What's on top of the windshield? Yeah. Grain bread. What about what's in front of the grill of your car? Perfect. So what you just memorized just now is what nutritionists call superfood. Not only do you remember this list so well, you can recall it forward, you can recall it backward, or randomly, right? So what in the wheel? What is the wheel at this point? Sweet potatoes. What's in your trunk? Fish. What's in your exhaust pipe? There goes my point. You can remember it in any order you like now. So essentially, all of these memorization techniques work this way. You're combining something that you are so familiar with something new, and then combine them to give you a better way to retain information. So far, so good. Perfect. So, let's see. So then at this point, I will move on to the second part of the presentation, which is when I talk about these memorization techniques. So the first one I have here is called the PEG system. This system uses numbers, which is something that you should have in your long-term memory, and then attach them to things that are rhyme or the shape. So for example, for one, I would remember that as a pencil, because pencil shaped like a number one. For two, I would remember a swan, shaped like a two. And then for three sounds like a tree, so tree and three, similar. Four is, of course, a chair, and then five is your hand, and so on and so forth. So this method is good for when you try to remember a list that has to be in order. So for example, if you have a grocery list, and you know where they are in a grocery store, and instead of going back and forth inside the grocery store, you want to go buy that list, this would be perfect for. So for example, let's say you need to buy apple, bread, and milk. Then what I would do is I would first imagine the number one, right? That's the pencil. I would imagine a pencil with a very big apple-shaped eraser. Then for two, I would then use a swan eating bread. And then for milk, I would imagine a carton of milk right next to a cat on the top of a tree. So essentially that's how that one works. Next one is called Memory Palace. This is probably one of the more famous, if not the most, one of the more famous one. It's called the Memory Palace, or sometimes the Mind Palace. It is most popularized by the show Sherlock, and it is mentioned quite a number of times on many different documentaries on Netflix that talks about memory. So this is essentially a broader version of the car example that I gave earlier. But the idea is the same. You use your place of interest that's already in your long-term memory and attach it to the new short-term memory. Now, just because there is the word palace in the name doesn't mean that you have to, own a palace to use this, right? As a matter of fact, at this point in my life, the best I could do is, a trailer or a house. But if you are someone who have been living in a palace and can use it, it works out perfectly too. And perhaps we should talk after the presentation, because I would like to learn how to make enough money to live in a palace. Now, so that's one way, to use a physical location. Another way to use this technique is by using a route that you are familiar with. So for example, due to my health not being what it should be for a relatively young guy, I recently started to go to the UREC in order to continue eating the things I like to eat. So for the past several months or so, my morning routine has been more or less the same. It started out with the UREC, then back to my car, and then to work, which is at Nicholson. So here's an example of me using that route to memorize the order of planets of the solar system. So of course, my morning start out at UREC, where I try to build muscle. Muscle starts with an M, so does Mercury. I then walk back to the car to drop off my stuff. This is also happened to be the same place where some idiot violently backed into the headlight of my car that one time. Violent, start with a V, so does Venus. And then as I start walking to work, I first cross a bridge. And under the bridge there, every now and then, these long-legged white birds that remind me of egret. Again, egret, same thing as Earth. And then the next place that I have in mind is the ECA, East Campus Apartment. Fun fact, that's where I used to live for my junior year. And the one thing that me and my roommates like to cook during that time is meatball spaghetti, meatball Mars. The next location is the LaVille dorm. My girlfriend then, which is fiance now, used to be an R8 there during her junior year, junior, Jupiter. The next thing is, of course, the stoplight on Highland Road, stoplight, Saturn. And the next place I have is Uranus, and that's the life science building. Again, the same girlfriend that I had then. Once become unconscious after seeing some mice get decapitated, unconscious, Uranus. The next place, Student Union, where I get noodle for lunch every day. So noodle, Neptune. And finally, Nicholson is where most of the physicists work at. Physics, Pluto. Sounds good? So, memory palace. Next, we have the image and name technique. As usual, you use something that you familiar with and combine it to the names. In this case, you make a visual image of a person's name that can help you remember it. Again, these techniques work either by an image or an intense emotion, right? And that emotion can often be something so ridiculous that you cannot get it off your mind. So for example here, I have two names. One is Rose. That's obvious, right? You remember the person's face inside of the rose. Next is Clark. I would imagine the same person whose name is Clark with some cake because, you know, Superman, whatnot. So beside image, you can also use the example. We have the phonetic number system. So this technique uses, or rather associate numbers with different letters of the alphabet and use them to create words and story that you can then visualize. So for example, what I have here is, it sounds very convoluted, but once you get used to it, it's very useful. So for example, you would associate 0 with the letter S or anything that makes the S sound or the Z sound. So like shoes, the S at the end of shoes would be 0, represent 0. And then T, like the, or the letter D, that's 1, and so on and so forth. So for this talk, I was, well, or rather, when I read the book on these memorization technique, like a good scientist that I am, I was very skeptical. I didn't think it would work. Let's see. Yep. So if you read these sentences, they are nonsensical, right? But through these sentences, I can now remember the first 100 digits of pi. First, let me prove that I remember these sentences first. So the first one is, oh Lord. I try to remember this. Let's say, let me put this out there first. I memorized this 3 weeks ago, and it took me 15 minutes to remember these, as well as the number to the sound thing system. Then I didn't practice it again until probably 2 hours ago. So bear with me. First sentence. My turtle poncho, will my love pick up my new mover ginger? Second sentence. My movie monkey plays in a favorite bucket. And last one. Have a baby fish knife, so Marvin will marinate the goose chickpea. Right? So now I prove to you that I memorized this, and in the perfect world, I will now convert them to the first 100 digits of pi without looking at the sentences again. But as I tested this 2 hours ago, the conversion rate is still quite a long time. So in the interest of time, let me first show you that these are the same sentences. No funny business here. So, just sentences. I will now convert this to the numbers to prove that these things work. So, in order, we have 3141592 5358 97932 384 6264. 338 327 9502 88 41971 69399 3751 05820 97494 and 4592307 81640 628 620 899 8280 34525 34211 7. Oh, okay. 70679. There we go. So these things work, and I hopefully convince you at this point that they work. So again, just to reiterate, there are 4 techniques that I've gone over tonight, and that's the peg system, good for lists in orders. The next one is a memory palace, good for essentially almost everything. Next one is image name, good for trying to, if you're in a interview or something like that, and you try to memorize someone's name, this is what it's for. And the last one, if you try to remember the number, this is the perfect system for it. Okay. Oh, I see. So I was supposed to have the book here. All of my information I got from a book called Unlimited Memory. Since I got most of my information from it, I thought I'd give it a plug here. It's not a sponsored talk or anything. I'm not getting any money for this. So with that, I would like to end the talk here. And if you have any question, I welcome it. Sounds good.
All right. Let's go ahead and open it up for questions. Jude, starting off strong.
Dragonite. Uh-huh. So the question is, what memory technique is best for trying to memorize a lot of words, essentially, right? For that, I would say the memory palace would be good for it. As a matter of fact, that's what I use to memorize those random sentences. For example, the first sentence was, my turtle poncho, will my love pick up my new mover ginger, right? So what I imagined was when I first walk into my house, I use the house as the long-term memory source in this case. My room is right after the door. So as I look to the door handle, the first image I see is, this is going to sound bad, a poncho made out of turtle shell. Then as I walk into the room, the first thing I see is my friend Will. And next to Will is my fiance, which is my love, hopefully. And she's picking up some red-headed mover guy. And the guy is shiny, which is new. So if you're trying to remember a lot of words like that, I think the mind palace is the perfect technique for that, yeah.
So when you translate the sentence to the number of pies,
yes.
Can you show that flow of in your head?
Yeah. So let me go back to, do I need to repeat that question or? Okay. So, let's do the first sentence here. M, remember M starts for M means 3, right? So that's what I have there, 3. Y is not in the system, so I can ignore that. Next thing I have would be the letter T, which is 1. So 3, 1, the next one would be R, which is 4. T again for 1, and L for 5. So 3, 1, 4, 1, 5 there. Next one is Poncho. P is 9. N is 2. NH sound is 6. So CH is for 6. Will, W and I doesn't count. And in my system, any double letter only counts as one letter. So the 2L counts as one number 5. Next is again mine, which is again 3, and then L again is 5. V is 8. So 8 is any V sound or F sound. So V is 8. Pick up, P is 9. The K sound is 7. Up, the P again is 9, and then 3. The new is 2. Mover is 3, 8, 4. And ginger, again, the G here has the Ch sound, right? So that's 6. So you have 6, 2, 6, 4. That's your question, right?
Yeah, yes.
Okay.
Well, I was not aware of the missing letters or skipping letters.
Right, yeah. So we only keep track of these sound and letters. Yeah.
Okay.
All right, any other questions for our audience here?
So for oh my gosh. So is there a way that you can get like overloaded on using these techniques? Like it just like you maybe you use the technique the same way at the same time, or you use it too many times and it doesn't work.
So what I present here is a tool, right? And with any tool, your efficiency comes with how often you use the tool. In terms of overloading them, I don't think it's possible. It just depends on how good you are coming up with story, right? So the example would be the phonetic example that I gave there. Those sentences took a bit of time to get there. You're gonna have to come up with something that you can remember for, a good amount of time. Yeah.
Also, I'm representing TEDx and TED Talk, and you are being served, and I will see you in court.
I'll see you there.
Also, that was a joke, so I don't get sued for fraud.
All right, any other questions?
That's it. Yeah.
So if you try to throw your word salad in there, ChatGPT,
Yeah.
right?
Yep.
I didn't know what you're saying.
Not yet. So when I try to come up with the sentences, I try to give it the system that I'm working at, and I told it to give me these sentences with these letters in order, and it fell like miserably. It couldn't do it. Yeah. But one day it's improving fast, so who knows?
Next question, anybody else? Okay. Thank you so much. We'll give another round of applause. All right, so our next, hold on. There we go. Okay, now the moment we've all been waiting for, our trivia answers. So hopefully you guys enjoyed our new style of trivia, moon or pancake or frying pan or cannonball. Hopefully it was challenging but fun. So we'll go ahead and go over our answers for that. Just give us one moment. Also, it was really impressive, all the numbers of pi, so. Okay, sorry, bear with us. There we go. All right. So, which of these images shows a pancake? It is B. Can you name this moon? It is Io. Can you name this moon? It's a pancake. Which of the previous names was not the name of a moon? They're all moons. Including Margaret, yes. Which of these images is Jupiter's moon Europa? It is B. Can you name this moon? It is Tethys? Tethys. Can you name this one? It is a frying pan. So a little trick there. It's not a pancake or a frying pan. All right, how many pancakes are hidden here? We have 1, 2, 3, 4, 5, 6. So there's only one real moon up there, and that is our moon. And there's our little citation there. It was great. All right, I'll give it up.
Yeah. So I didn't make the photos of these pancakes. There's this famous book. It's not really famous, but you should all look into that book, which has about 60 or 70 artificial moons, which are all pancakes.
So good sources for our trivia. All right, so there's our trivia, which means we have winners. So as always, we'll have our 2 winners. All right, our first winner is Jude, extending his 2-month streak. And we do have another winner. We have Scott C. So if you have won, you can go up to our merch table on your way out and pick out your prize. All right, everybody go ahead and get those raffle tickets out. It's time for the raffle. All right. This one feels lucky. All right. We have 3, 0, 5, 0, 3, and 6. So that is 3, 0, 5, 0, 3, 6. Going once. 3, 0, 5, 0, 3, 6. Going twice. All right, not sold. You have another chance. All right, let's see if this one is a winner. 3, 0, 5, 0, 2, 7. That is 305027. Going once. And he's gone. So we'll have a third lucky ticket. I might just have to draw all of them here, I guess. I don't know. All right, let's do this again. 305. And shockingly, it is 026. Is it really you, Jude? All right, I'll draw another one because we do have, no, you'll give it away. All right. Okay, how about I draw another one? Jude is willingly give away his trivia. All right, let's try this one more time. 305 018. It's me. All right. This is number 5, trial number 5. All right. 305 029. Is that you? Woo! All right. 3050229. All right, let's give it up for our raffle winner. I think that's our record for the most raffle tickets drawn in an AOT show. So thank you so much for coming out tonight. Make sure you tip your bartenders, tip your servers, and we will see you in March. Thank you so much for coming out.